In the previous video, I tried to explain the process of renormalization to dimensional regularization, and I got a lot of things wrong. And I'm here to make amends for that in a way. So we start off at the same point, start off where we did start off in the last video. And we see that when we try to derive a classical-like equation from our generating functionals, we get an extra quantum effect, which is actually divergent. So the way that we rationalize this is that instead of saying this is the Klein-Gordon equation, this is the Klein-Gordon equation, we say that this mass is actually a mass that we can't measure in the lab, and when you pair this mass together with this divergent quantity, you get your old mass that doesn't have the B subscript. And the B stands for bare, B-A-R-E, and it basically means a non-renormalized quantity. And that's something that you can't measure, and something that that counters the divergence because of the quantum effect, to give you a finite term that you can actually measure in the lab. Yeah, that's the philosophy of renormalization. And so we have to try to find a way to express this infinite term so that we can define this to be infinite in a way that so-called cancels this out. So that's what we need to do. We need to evaluate this Feynman propagator. Right, what I've written here is, all the way on the left is the Feynman diagram, and this is the Feynman diagram of a one loop. It's basically a particle coming in, goes into a loop, and then it comes back up, and the loop has momentum q. And this is how the Feynman propagator looks like. That corresponds to this Feynman diagram, and we use the slash notation again, like we used in the previous video. And here what we do is we can consider evaluating this integral in Euclidean space. Right now we are in Minkowski space, and we like to evaluate this in Euclidean space to get rid of this plus IE prescription that we need to do because of the nature of the green function. So what we do is we consider a Wick rotation, and that will basically give you a factor of I, and then that takes away this. We don't need this anymore, and it gives you a negative sign in the Q. And because there are two negatives in the denominator, what we can do is can bring the negative out, and then we just change this to plus, and we will include an E subscript to denote it that is in Euclidean space. So that's how our integral looks like now, once we've done the Wick rotation. And now we can, since we are in Euclidean space, we can consider our spherical symmetry as we do. This is the expansion of this integral in spherical coordinates. So this looks very similar to what you might get in 3D. And in 3D you might recall something like this, plus some angular components which you just write as d omega. And put a 3 subscript to indicate that we are in 3-dimensional space, and here is a 4 subscript to indicate that we are in 4-dimensional space. So you can see you have the radius square coming out. Here you can write this as x. Yeah, so you have the radius coming up, and basically it's the same thing here, but it's absolute because we use the same symbol here. And we put it to the power of 3 because now we're in 4 dimensions. Same thing here, and angular components we can just ignore because they're just factors of pi. Right, so let's do that. The 2 pi to the power of 4 factor remains, so I'm just taking it out of the slash notation. Yep, that's how it looks like. And what you notice here is that if we take the integral from infinity to negative infinity as we do, and one more thing to note is that in considering the relativistic scenario, so our momentum goes from infinity to negative infinity, because relativistic momentum is multiplied by the Lorentz factor, and that goes to infinity as v approaches. So we take negative infinity to infinity, and we notice that this term actually is proportional to a singular power of QE. Because you have 3 powers on top, you have 2 powers below. And this integral diverges as you take the integral across all space. So that's where the issue lies. That's how we've shown that this is an infinite quantity. So how can we go about dealing with this? Well, the first thing that we're going to talk about is a superficial degree of divergence, and that allows us to tell almost at a moment's notice what Feynman diagrams actually give us these infinities. I'm going to erase the board now, so I'm going to pause the video and then I'll be back. Alright, let's continue where we left off. D stands for the superficial degree of divergence, which we talked about. And we're going to say that it's equal, we're going to define it to be equal to the powers in the numerator of the integral minus the powers of the denominator. And this is easily expressed if you take the number of independent loop momenta multiplied by 4 and take the number of internal lines and multiplied by 2, and you take the difference between them. The reason this happens is because the number of independent loop momenta is basically the number of times you're integrating over Qn, and the number of internal lines is basically independent or not the number of loop momenta there are, and these actually contribute to the denominators. Basically these terms. And the reason 4 minus 2 is because the 2 is easy to see, it's from this, because it's in the denominator. The 4 comes actually from here. And you might be wondering why we take 4 instead of 3, because previously we showed that there's a power of 3 that comes out in our Euclidean, when we consider it in Euclidean space. But the reason is because even if there wasn't the 3 power here, if you integrate just a factor of 1 on its own, you get 1 power on your own in the result of the integral. So that's why we take 4 and we minus 2. So that's how you get your divergence. So for example, if you want to go back to case of a one loop, we have 4 powers in the numerator, one coming from this, one coming from the numerator itself, the 3, and then we have the square in the denominator. So the result will be proportional to q squared. Okay. And that diverges. Yeah, so this is the basic formula. And I'm going to erase all of this, and we're going to try to expand this out and take it for a specific instance of 5-4 theory. Here I've drawn a contribution that is divergent, and I would like us to consider how to reduce this expression into something that just requires one term. Because now we have 2 terms, we have an L and an I, and if we could simplify this even more, it would be great. So here we'll introduce what is known as Euler's formula, and I'm going to write it a little bit differently to what you might see. And what this says is that for a graph like this, the number of corners minus the number of edges plus the number of faces is equal to 2. I won't prove this result. This is Euler's formula for connected graphs. And when we say graph, we mean something like this. So let me just identify the components of a graph for you. And I am marking off our vertices, but I'm also going to mark off our external points. And these external points and vertices in the context of graph theory are considered corners. So when we, let's say, take a 3-dimensional object, for example, you have the cube, and these are the corners. Yeah, so on the cube we have 12 corners, because we have 8 corners, sorry, 8 corners, and we have 6 faces, and we have 12 edges. Edges run this way. They are suspended in between the corners. So if you think of this diagram as a kind of net, a net of a 3-dimensional object, then you might see that there's one face here, there's another face here, and there's another face here. And additionally, there's one more face encompassing the outside. And the way you can visualize this is, if we were to take this and take it out the board, and we were to make a wire frame of it, and we dip that wire frame in soap, and you take it out of the soap, you might notice that there will be bubbles suspended in between here, but there will be also a bubble encompassing the whole outside. So in reality, you have 1, 2, 3, and we have 4 faces here. So for this graph, you have 4. And for corners, as we talked about, we include the external points along with counting the vertices. So here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 corners, and edges are basically the lines that are suspended in between corners. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can verify that this formula is indeed correct. So, as we said, the faces are kind of special. You can see that there are 3 loops, but we have 4 faces. So, in fact, the number of loops is equal to the number of faces minus 1. This is an important result. So loops is equal to the number of faces minus 1. And in the context of our Feynman diagram, a corner, you can take it as the vertices plus the number of external points, and edges are the number of internal lines. Internal lines with also We do include external lines, of course we do. Yep. So the number of corners is the number of vertices and external points. The number of edges is the number of internal lines plus the number of external lines, which is equal to the number of external points. And the face, number of faces from this relation is equal to L plus 1. So let's just plug this in. So we get V plus E minus I bracket plus E plus L plus 1 equals to 2. Okay, and the E's minus off, we get V minus I plus L equals 1, because the 1 minus off on this side will become 1. Yep. Okay. And in fact, we can rearrange this. L is equal to I minus V plus 1. And now if we sub this all the way into here, we should get 4I minus 4V plus 4 minus 2I. Okay, I'm gonna erase a little bit more, so I'm gonna pause. Right, we're back. And if we evaluate this, obviously this 4I minus 2I, we get 2I plus minus 4V plus 4. And I'm gonna actually write this write these two terms in a bracket. And this is actually the number of external points, if you think about it, because the number of connections that you can make on each vertex is 4, and the number of connections that an internal line makes is 2. So each internal line occupies 2 connection points of every of the vertices, which means that if you take the number of connection points minus the number of connection points that are used by internal lines, you will get basically the number of connections used by external points. And the number of connections used by external points is equal to the number of external points. So you can write that as 4 minus E. And this is basically your formula for superficial degree of divergence in 5/4 theory. I'm gonna erase all of this again, and I'm gonna make more comments about this. Alright, I have this boxed up, and I've written that this D is called the superficial degree of divergence. We'll discuss in a moment why it's called superficial. And before that, we would like to talk about the degrees of divergences, because this is a degree value. And we'll talk a bit about what it means for different ranges of D. When D equals 0, you basically have more powers in the denominator than in the numerator. And that basically means no divergence. So that's a good thing. We would ideally like to see that. And when D equals 0, it means that we have equal powers in the numerator and equal powers in the denominator. However, the issue with that is that means our integral looks something like this, because there's one power here and there's one power to cancel it out in the denominator. So D will end up as 0. But obviously when you integrate that, you get a logarithm, and this is a divergent quantity also. So what we call this logarithmic divergence. And when D is more than 0, It's basically what we saw all the way back. For example, this. We see that the integral looks something like this, and this diverges. And we call this a quadratic divergence because we have a power of 2 here. And for example, if we have another integral that has maybe q squared here, then you have a power of 3. It will be called a cubic divergence. And you have a quartic divergence, a quintic divergence, and so on. So you shall just term it as a xd divergence. And that's what these degrees are. Finally, we can talk about why this is called superficial. And the reason it's called superficial is because it doesn't actually reveal everything about the divergence of a diagram, nor does it even reveal fully if the diagram is divergent. So let's consider a diagram maybe something like this. With, let's say, 6 external points. So we have one here, one here, one here, one here, one here, one here. Right. And if you do the formula for d minus 4e, so you have 6 external points, you get negative 2. But it's very obvious that this diagram is divergent because of this loop right here. So what's going on? Well, the issue that's going on is that while the diagram doesn't look divergent, it actually is divergent. So that's why we call it superficial. So even though the degree might suggest it's not divergent, it might be divergent. So how can we fix this? Well, we shall fix this by considering another scenario. So let's consider another 6-point function. But this time, maybe we don't add any loops inside. So what happens if we don't have any loops inside? Well, obviously this is now not divergent because there are no loops inside. But what if we want to replace one vertex with a loop? So let's say we replace this one with a loop. Like that. Now d remains as negative 2, but we have a divergent loop in the middle. So what can we say? Well, if we consider amputating the diagram in a manner such that, because this is not a 1pi, we can say let's amputate the diagram a little bit like that. So we cut this off, and we amputate the diagram here. Then what do we get? We basically get, we reveal the divergent diagram, and this diagram has d equals 2. But as d equals 0, sorry, a log divergence. So here comes the theorem. The theorem is that if we have a diagram, and if we can split it down into its sub-diagrams, like this is a sub-diagram of this, and all these sub-diagrams have a superficial degree of divergence less than 0, only then can we say that the whole diagram is not divergent. And this statement is actually a theorem, and it's called Weinberg's theorem. So I'll write it down. And this is Weinberg's theorem written out in word form, which says if the superficial degree of divergence of the main Feynman diagram and all sub-Feynman diagrams are less than 0, then the integral will converge, or rather it's non-divergent. And we'll end on this theorem, and that shall be the introduction to our motivation for renormalization. I'm going to make this into a multi-part series because I realized over the filming of this one part that it's very, very long. I've actually written quite a lot of notes. There's another whole booklet of this. And maybe I might not even present it on the board. We'll see how. For now, we'll just cover this, and after this we are probably going to cover a few methods of regularization, including our high energy cutoff, our covariant cutoff that we presented. Also present Pauli-Vilas regularization and dimensional regularization at the end. And then we'll calculate it for a few 1PIs, we will calculate it for 2.1 pi, and we also calculate it for 4.1 pi. And we also end touching a bit on how virtual particles can actually become on-shell and real particles. Yep, that's about it for now. Thank you very much.